Offered by the Mathematics Club of IIT Madras. I am Navin, one of the heads of the Mathematics Club, and along with me, Karthik Kashyap here. Our beloved KK is another head of the club. Over the next few weeks, we'll be exploring a lot of mathematical landscapes that will challenge your understanding and your intuition of a lot of fundamental math. Today, we'll be starting off with projective geometry, where the structure of thought is as important as the structure of space. We are glad that you're here with us on this journey. Before we begin, I'll just let you know about some details. So the session is being recorded and it will be uploaded to our YouTube channel so that you will be able to watch them later on. And attendance will be taken in live during the meeting in between at some random interval. Attendance is mandatory for certification, and I'll also set some ground rules. So we are allowing participants to unmute themselves and ask doubts in between. However, in order to ensure that all of this happens in an orderly fashion, just raise your hand before you wish to ask something. And as and when important concepts are taught, our coordinators will also pause for a few minutes in between to ask for doubts. We also have some interactive content lined up in the between the sessions. We'll have some Slido polls and whatnot. You'll be seeing the QR code for the Slido poll in the meeting itself, and we'll also be sharing the code to join the Slido poll. So if you are on your phone, we recommend you to just use the code. And if you are watching the session from your laptop or any other desktop device, then it's simpler for you to just scan the QR code. Anything else that you would like to add, KK?
Yeah, nothing much.
All right. I'll hand it over to my coordinators, Smithali and Bhavi, who will be taking today's session on projective geometry.
Yeah, good morning, everyone. We'll start with the first session of summer school by Mathin, points, perceptions, and projections. So the aim of this session is to help you understand how we formulate geometries, and we'll take you through the applications as well, like right from formulation to applications. In particular, we'll do this by looking at projective geometry. So you deal with various geometry problems in your high school or college math, like right from similarity problems to coordinate geometry, conics, and all. So can we come up with a set of rules that define how we make Euclidean space out of the objects, lines, points, and curves? So you have lines, points, and curves, and now how do you define them in such a way that you create the two-dimensional or three-dimensional Euclidean grid or space? So, oh, wait, I did my bad. So how do you do this? So the idea is there are a set of rules called as axioms, which are self-evident truth, and any theorem in the in the geometry can be proved on the basis of these axioms, and there is no proof for these axioms because they are self-evident. So what Euclid did was Euclid came up with this five set of rules and but these, like for example, if you take one intersection 5 and one union 5, then you can replace them with 1 and 5. So these are the historical rules which he came up with. If you go online and search, you will find more understandable rules. So let's go through each of these exams one by one. So first exam says that a straight line may be drawn from any point to any other point. So you pick up any point in my room and pick up any point in Bhavi's room, and you can draw a straight line through that. Second phase, that the straight line you can extend it infinitely to make an infinite line out of this finite straight line. The third says that you can take up any point as center, and you can have any radius, and that will make your circle. Fourth says that all right angles are equal, just like the formula of S2 is same everywhere. All the right angles anywhere in the space, Euclidean space, would be equal. The fifth one says that suppose you have this line and you draw two other such lines which are at an angle less than 90 degree with the initial line, then the intersection of both of these lines will also be at a point on the same side of that line. So now when you will combine this fifth with first and fourth, what you get is the parallel axiom. Like there exist lines which would never meet, right? So this is about Euclidean geometry. Uh, then what are non-Euclidean geometries? So Euclid defined his space in such a way that he can do measurements, like you can measure a line, you can measure area, and so on. But I'm not interested in measurement right now. What will happen if I'll squeeze the space or I'll fold it or make holes in the Euclidean space? What happens when you break the Euclid's axioms? So these are some geometries which are not Euclidean. For example, hyperbolic geometry, projective geometry, which we'll see through today, then elliptic geometry and absolute or neutral geometry. For intuition, elliptic geometry, lines are great circles. So, like Earth has latitudes and longitudes, right? So, latitudes and longitudes are the great circles of Earth. So, you take your Euclidean space and you convert lines into a great circle. So, there will be a 2D sphere kind of model. So, that's elliptic geometry. Then, absolute or neutral geometry. So, this is kind of a raw axiomatic geometry where you remove the parallel axiom from any geometry, and then the raw basic axiomatic geometry is absolute or neutral geometry. So, projective geometry. Uh, what happens when you squeeze a line into a point, or you stretch a point into a line? So, kind of like 3D to 2D, 2D to 3D, and so on. But you can't squeeze any random line into any point belonging to that line. You need to come up with some concrete definitions, right? So, do you guys have any idea, suggestion? Put it in the chat, or yeah. How can you formulate squeezing a line into a point? Okay, fine. I'll go ahead, I guess. So, like Euclidean space had some axioms, projective space also has some axioms. Uh, so, likewise, Euclidean space, you have any two distinct points, and they are incident with exactly one line. Then, any two lines will intersect in at least one point. So, does this mean that parallel lines don't exist because any two lines are incident with at least one point? Then there exist 4 points of which no three are collinear. So for example, you can see these 4 points, no three of these are collinear. Uh, Coming to the next example, three diagonal points of a complete quadrangle are never collinear. What's a complete quadrangle? Basically a quadrilateral with the internal diagonals or any two of the diagonals included. That's a complete quadrangle. So you consider these also as the sides. So what these theorem says is that the intersection of any two opposite sides, for example, you take PQSR, they intersect in W, PSQR, they intersect in U, and PRQS, they intersect in V. So UVW will not be collinear. Now, why is this an axiom? As I said earlier, you take intersection of any two and you take union of any two, you get a different set of axioms, but it's still valid. So this can be a theorem as well, and at many places you will see that this is a theorem and the set of axioms considered is something else. So yeah, this is there. Uh, Coming to the last axiom of projective space. So you consider a hexagon with its vertices alternatively lying on some lines. Now these hexagons look pretty weird because they are not like a regular convex hexagon, but they are defined in such a way that their vertices would lie alternatively on two lines, as you can see here. And it says that then the intersection of pair of opposite sides are collinear. So you can draw it this way or you can draw it this way. Can someone tell me what is wrong with this diagram? Like B3, C3, A3 are still collinear. Anyway, even the coordinators can answer, it's fine. So this is a very easy question. Just read this and what's wrong here. Uh, okay, so basically this diagram does not stick to the theorem, the statement itself. Like the points of hexagon does not lie alternatively on two lines. So my point here is that the converse, uh, the converse could be true without like this. This statement would also be true for other cases, but that does not mean that it will be true for all cases which don't satisfy this. So just a slight part of rigor, and we had like the session to be interactive. So please answer. So what's so special about projective geometry? What makes projective geometry? Projective geometry is the principle of duality. So in any theorem, in any axiom, anywhere in projective geometry, if you replace a line with a point, uh, it remains consistent, it remains true. So for proving this, if we prove this principle for axioms, it would mean that it has to be true for whole of projective geometry because anything in projective geometry can be proved using axioms. So let's consider all the axioms one by one. So the left side is the original axiom and the right side is its dual. So any two distinct points are incident with just one line would mean that any two distinct lines are incident with just one point. If you see the first and the second axioms, basically for proving this, you prove it using the second original axiom, and proving this, you prove this using the first. Like they are the same thing, right? Any two distinct points are incident with at least one line, and any two distinct points are incident with at least one line. Third one, there exist 4 points of which no three are collinear, would mean there exist 4 lines of which no three are concurrent. So, for example, consider these 4 lines. No three of these are concurrent. The next one, the three diagonal points of a complete quadrangle are never collinear. So the three diagonal lines WU, PR, and QS for complete quadrangle are never concurrent, which also seems intuitively right because if you have a quadrangle, be it convex or concave, either one of the diagonal will be inside, two will be outside, or one will be outside, two will be inside. So they would never be able to be concurrent because you are considering the quadrangle, right? So, and the last axiom, it's dual. You shall prove it in your assignment. Uh, now, you guys should put your name in the chat for marking your attendance. And meanwhile, if you have any doubt, put those doubts as well or unmute yourself. Okay, cool. So now Bhavi will take over.
Hello everyone. Now we'll continue with homogeneous coordinates. So how do we represent coordinates in Euclidean geometry? What coordinate system do we use? Well, we use Cartesian system of coordinates. In Cartesian system, we use pairs such as x, y in 2D or triplets such as x, y, z in 3D. While this system is intuitive and practical for many purposes, Cartesian coordinates fall short where transformations like perspective projections, points at infinity, and unification of geometry are required. Unification of geometry are required. Homogeneous coordinates are ubiquitous in fields like computer graphics, computer vision, robotics, and advanced geometry. Let us see what they are. So, homogeneous coordinates extend Cartesian coordinates by introducing an extra dimension. So, a point in 2D is represented by x comma y, but in homogeneous coordinates it becomes x comma y comma w in where w is not equal to 0. The corresponding Cartesian coordinate is then represented as x upon w comma y upon w. Similarly, for 3D, a point x comma y comma z is represented as x comma y comma z comma w, and the corresponding coordinate in Cartesian can be represented as x upon w comma y upon w comma z upon w. Here w is the weighing factor or the scale factor. In general, we can say that a Cartesian coordinate we can say that x comma y is equivalent to kx comma ky comma kw, where k is not equal to 0 in homogeneous coordinates. Thus, homogeneous coordinates which are scalar multiple of each other form equivalent classes, and multiple homogeneous points map to same Cartesian point, such as like if there's a homogeneous coordinate such as like 4 comma 3 comma 1, it is equivalent to 2 comma 1.5 comma 0.5, which is equivalent to 8 comma 6 comma 2, and they all represent the Cartesian coordinate 4 comma 3. Now, what if w is 0? Homogeneous coordinate x comma y comma 0 corresponds to a point at infinity in direction y upon x. This represents the point of intersection of family of parallel lines with slope y upon x. This is a key principle in projective geometry. Now, why does it work? Homogeneous coordinates turn affine transformations and projective transformations into linear operations in higher dimensional space. This unification is critical in projective geometry, where intersection, collinearity, and incidence are preserved under projection. Now, there's a reason why we can't use Cartesian coordinates. Cartesian coordinates are not sufficient for projective geometry because they cannot represent points at infinity, which are essential in projective geometry. Projective geometry deals with concepts like lines lines meeting at infinity, which require a system that can handle these points at infinity. Homogeneous coordinates, on the other hand, can represent both finite and infinite points using a consistent system. Also, linear transformations such as translations, scaling, and rotation can be represented by matrix multiplication. However, there's a catch. Translation is not a linear transformation in Cartesian coordinates. For example, if we have a point x comma y and we need to shift it by a comma b, where we are shifting x coordinate by a units and we are shifting y coordinate by b units. So the result is x plus a comma y plus b. This is the new coordinate, but there is no matrix transformation which allows us to convert x comma y to this coordinate using a 2 by 2 matrix. This inability complicates algorithms, especially in graphics and computer vision, where combining transformations into a single matrix is desirable. The natural setting for homogeneous coordinate in projective space is denoted by p raised to power n, where n is the dimension. In p square, every point is an equivalence class of 3D vectors x, y, w, where we discussed earlier that, so in P square, uh, every coordinate x, y, w. Please note that P square is the projective space in 2 dimensions. So x, y, w is similar to kx, ky, kw, where k is not equal to 0. So this means that points in projective space are not individual vectors, but entire lines to the origin in the real space of dimension n plus 1. Here n is the dimension of projective space. So in this case, they are lines in R cube or real space, 3D space. This point of view is critical because rather than viewing a point as a fixed location, we see it as a direction in higher dimensional space. This conceptual shift provides deep geometric and algebraic insights. Projective space is compact. Projective space is compact, which means it includes points at infinity, and projective transformations, which are linear maps in homogeneous coordinates, preserve incidence relations, which are points lie on the same lines. Let us see how do we convert Cartesian points to homogeneous coordinates. Let us take a point x, y, add a third parameter 1 to it. If we allow this parameter to attain the value of 0, then it is the homogeneous coordinate of the given Cartesian coordinate. Let us see with an example. So let us suppose we have a point 4, 5. Now the corresponding homogeneous coordinate can be made by adding another parameter which is equal to 1. So 4, 5, 1 is the corresponding homogeneous coordinate. And when we change this 1 to 0, we obtain its corresponding point at infinity, which is 4, 5, 0. Now this point is the intersection point of the family of lines with slope 5 upon 4. Yeah. So in 2D projective space, a point is represented as a vector in the form of x upon y, x, y, w, and a line is a vector a, b, c. A point lies on a line if ax plus by plus cw is equal to 0. This can also be represented as when if we represent the point as if we represent this as a one-dimensional vector, then P into L transpose should be equal to 0. So if this is 0, then the point lies on the corresponding line. So this mirrors the equation of a line in Cartesian form, but extends it to projective space by incorporating the third coordinate w. This symmetry allows us to treat points and lines on equal footing and enables algebraic manipulations using matrix and vector operations. The key insight is the equation ax plus by plus cw is equal to 0 can be interpreted in two ways. As the equation of line a, b, c passing through a point x, y, w, or as the equation of a point x, y, w belonging to a line a, b, c. This symmetry is the foundation of duality. In a sense, the roles of points and lines or planes in 3D are interchangeable in projective geometry, and any theorem proven using one interpretation can be transformed into a dual theorem by swapping point and line. Moving on to coordinate of point of intersection of two lines. To find the point of intersection of two lines, let us say we are given two lines L, A1, B1, C1, and L2, A2, B2, and C2. These are the homogeneous coordinates of two lines. So to find their intersection, we can simply take the cross product of L1 and L2. This cross product would give us the intersection point. So can you guess how do we find the line passing through 2 points? We just discussed this. So yeah, well, duality is conserved. So if we take cross product, guys, no, like I meant that if we are given 2 points P1 and P2, P1 is x1, comma y1, comma w1, and P2 is x2, comma y2, comma w2. So using these two, how will we calculate the equation of line which is passing through them? Yes, that is correct. We take the cross product because duality is established. So L would be equal to P1 cross P2. These operations are defined even when the points or lines are at infinity. This contrasts with the Cartesian geometry, where special handling is required for cases like parallel lines. In homogeneous coordinates, uh, this is not just a philosophical idea, but a concrete algebraic reality. Both points and lines are 3D vectors, and incidence relations are symmetric. For example, if a point lies on a line, then the line passes through the point. This symmetry makes homogeneous coordinates an ideal tool for formal geometric reasoning. So let us look at a few questions. Can you solve this question? I'll wait for 1 more minute. We can now let us discuss. So we can see that the ratio, uh, yeah, if we calculate the value of k, then while comparing the x coordinate, the value comes out to be 2. While comparing y coordinate, the value comes out to be 4 by 3. And while comparing the value of the w, it comes out to be 1. So since no value of k agrees with each other, they are not the same set of homogeneous coordinates. So try this one. There are 3 parameters. There should be 3 parameters. Check once again. Yeah, Sarthak is close. Yeah, Sarthak is right. Yeah. So we can simply take the values of A, B, and C. The value of A is 4, value of B is 5, and value of C is -6. Yeah. Last question of this section. Find the points of intersection for lines with coordinates 4, 3, 5 and 3, 6, 7.
Okay, guys, if you are interactive, you will get brownie points in assignments, and assignments are kind of hard. So, yeah, interactive.
So did anyone try this question? So let's
Bobby, there are answers in chat.
let's check their answers once. So the points were 4, 3, 5, 3, 6, 7. We take their cross product. I cap, J cap, K cap. So this comes out to be -9 I cap minus 13 J cap plus so -9 minus 13, 15. Rahman gave the correct answer. Sanjay also gave the correct answer. And Sohan and Pragya also. Good, guys. So moving on next to a fine plane. So a affine plane is a fundamental construct in geometry characterized by a set of points and a set of lines that satisfy a specific set of axioms. At its core, it's a two-dimensional affine space over a field, often visualized similarly to the familiar Cartesian plane, but abstracted and generalized to emphasize structural properties over metric ones like distance or angle. We define the axioms of an affine plane as axiom 1, uniqueness of a line. For any two distinct points, there exists exactly one line containing both. Axiom 2, the parallel property. Given a line L and a point P not on L, there is exactly one line through P that is parallel to L. Axiom 3, existence of non-collinear points. There exist at least 3 non-collinear points. These axioms define a finite incident structure or an affine geometry, generalizing Euclidean geometry by preserving notions of parallelism and collinearity. While discarding measurement concepts such as angles and lengths, parallelism is parallelism in an affine plane is an equivalence relation among lines. Two lines are parallel if they do not intersect. This is in contrast to projective geometry where all lines intersect, possibly at infinity. The parallel postulate ensures that every direction in the plane has a unique line passing through a given point. So, any doubts till now? Anyone has any doubts? Okay, so
Bhavi, the third point.
yeah, there exist 4 points, no 3 of which are collinear. So this clearly means that in a plane, if we can choose 4 points such that no 3 of them are collinear. So if we choose 4 points such that if we choose 4 points like these, we cannot make a line which passes through all 4 of them, right? Or even if yeah, so that is what it's basically saying, that there exist at least 3 non-collinear or 4 points, 3 of which are non-collinear. Yeah, non-zero coordinate. Uh, so now let us define an affine plane over a field F. It is denoted by uh, it consists of all the ordered pairs x comma y with both x comma y such that both x comma y belong to F, the field F. Lines in this plane are defined by linear equations of the form ax plus by is equal to c, where again these coefficients a, b, and c, they also belong to F, and not both a and b can be equal to 0. So one of them can be, but not both simultaneously. This affine plane satisfies the axioms above and provides the prototypical example of an affine geometry. Let us understand what affine transformations are. So an affine transformation is the function f from defined from a square to a square, which is basically a affine plane to another affine plane, and is of the form f is equal to ax plus b, where a is a 2 by 2 matrix over the field F and b is a vector in F square. So this is a 2 by 2 matrix in F, and b is a vector in F square. These transformations include translations, scalings, rotations over real or complex fields, and shear transformations. Affine transformations preserve parallelism, collinearity, ratio of lengths along a line, but not angles and distance. The set of all such transformations from the affine group, which is denoted by this is the affine group. Interestingly, an affine plane lacks a natural origin, unlike a vector space. However, we can impose coordinates using a chosen point and two linearly independent vectors. which form an affine basis. Looking at its structure, an affine plane over a finite field F. So we represent a finite field F as Fq, and the affine plane is denoted as A square over and Fq. It consists of all ordered pairs x comma y with x comma y both belonging to this field, and q is a prime power. Prime power basically implies that q is a prime number. It contains q square points, q into q plus 1 lines, and every line contains exactly q points, and each point lies on exactly q plus 1 lines. So let us see an example. So over F2, if we consider A square F2 has 4 points and 6 lines. Can you tell with how many points and lines will be there in F3? A square F3. Yeah. In this, how many points and lines? Yes. Vishit is right. Midul is also right. Karthik is also right. So F3 would have 9 points and 12 lines. Each direction or slope defines a parallel class of lines that never intersect, reflecting the parallel postulate. Unlike the Euclidean plane, the affine plane over a finite field is finite, discrete, and highly symmetrical. So looking back at the slide, it is mentioned that duality is absent in case of affine planes. Can you recall the reason of it? Submit it here if you want. Or type it in the chat. Both are fine. Yes, parallel lines exist. So this means that parallel lines do not, uh, yeah. So this means that parallel lines do not intersect ever. They remain parallel always. Yes, number of points and lines are different. So they remain parallel. But how do we make a projective plane from an affine plane? Well, we introduce a new concept, line at infinity. So the line at infinity is not a physical or visual line in Euclidean sense. It's an abstract geometrical object introduced in projective geometry to ensure that every pair of lines intersect at exactly one point. Till now, any doubts? Are there any doubts?
Oh, nothing in chat.
Okay. So, to make this true even for parallel lines, projective geometry asserts that all parallel lines do intersect, but they do so at a point at infinity. So, these points at infinity do not lie in the affine plane. They are added to it, forming what is called the projective completion. The set of all points with w is equal to 0 forms a line in the projective plane. So we present this line as L infinity, which is equal to all the set of x, comma y comma 0, which belong to the projective plane. So this is the notation of line of infinity. This is the set containing the points which lie on line at infinity. So each point x comma y comma 0 corresponds to a direction in the affine plane, and all the parallel lines in that direction intersect at this point in the projective plane. Thus, projective geometry resolves the issue of parallelism by compactifying the plane. It wraps up the plane so that every direction converges. So let us look at the significance of line at infinity. First is unifying geometric theorems. There are many theorems in Euclidean geometry about lines and intersection which come with uh, limitations such that two lines intersect, but it must be qualified that unless they are parallel, the number of intersection points between curves is fixed, requires exceptions when those intersections occur at infinity. So the line at infinity eliminates these exceptions by ensuring that any two lines intersect even if a point is not visible in the affine plane. This leads to a cleaner, more general version of the theorems, such as Desargues' theorem, which fails in certain affine planes due to lack of general intersection, but it holds fully in the projective plane. Then there is Bezo's theorem, which states that two algebraic curves of degrees m and n intersect in m into n points, counting their multiplicities, but it requires a projective setting to account for intersections which occur at infinity. Thus, line at infinity allows theorems to be stated without exceptions, giving geometry a more elegant, symmetric, and algebraically complete foundation. Then it is enabling duality. The much we talk, the less it feels. A remarkable feature of projective geometry is the principle of duality, wherein statements about points and lines can be interchanged. For instance, 2 points determine a line has a dual, two lines intersect at a point. 3 points lie on a line is the dual of three lines pass through a point. This powerful symmetry relies on the idea that all lines intersect, which, uh, which, made, which is made possible only after adding the line at infinity. In affine geometry, duality fails because parallel lines do not intersect. Yeah, in this way. By embedding the affine plane into projective one and including the line at infinity, we gain this point line duality. It becomes not only a conceptual elegance, but also a practical tool in proofs, transformations, and algebraic reasoning. Uh, then in a affine plane, not all transformations can be represented as matrix multiplications. For instance, rotations and scaling can be represented by 2 by 2 matrices, but translations require addition and cannot be incorporated into a single matrix transformation. Homogeneous coordinates introduced alongside the line at infinity resolve this by embedding affine transformations into projective space. So now using 3 by 3 matrices, we can represent all the affine transformations, translations, rotations, scaling, and shears as linear operations in homogeneous coordinates. This unification of all geometric transformation into linear algebra is crucial in computer graphics, robotics, computer vision, and geometry processing. It simplifies composition of transformations but enables efficient computation and symbolic manipulations. Last but not the least, as you can see in the video as well, it unifies the conics. This is probably the most beautiful aspect too. In Euclidean geometry, conic sections, ellipses, parabolas, and hyperbolas are all treated as fundamentally different due to their distinct algebraic forms and geometric properties. However, this distinction is an artifact of affine space. In projective geometry, once we add the line at infinity, all non-degenerate conics become equivalent under projective transformations. This means a parabola is just a conic that touches the line at infinity. A hyperbola is one that intersects it at two distinct points. An ellipse is the one that does not intersect it at all in the real plane. So this classification depends upon how conics interact with the line at infinity, revealing the apparent differences between conics that are simply differences in perspective. In projective geometry, they are all the same up to the projective equivalence. This insight is profound. What appears as diversity in affine space becomes unity in the projective space, with the line at infinity serving as the key to this unification. Points on the line at infinity, which are x, y, 0, are sometimes referred to as ideal points. So we can say that all of these points which lie on the line at infinity are ideal points, and the line itself as the ideal line. Yes. How does translation become a linear operation here? So we know that we cannot represent it as a 2 by 2 matrix. But in 3 by 3, what we can do is we can take, suppose we have to translate x coordinate by A and y coordinate by B. So we use the matrix 1, 0, A, 0, 1, B, and 0, 0, 1. If we multiply it to x, y, w, we obtain the translated, it's usually not w. We use 1 so that it can be easily converted in it can be easily converted in terms of Cartesian coordinates, because we know that all one. So if we do the matrix multiplication of this, we obtain the translated version of the coordinate. Is the doubt clear? I hope it is. So the points, and the line itself is the ideal line. These terms reflect the philosophical shift. Rather than limiting geometry to measurable, finite things, projective geometry includes the idealized behavior of directions and limits. Now, finally, let us look at some of the ways to construct line at infinity. So, there are 3 ways of constructing line at infinity. Let us consider each of them one by one. So using homogeneous coordinates, in affine geometry, a point is represented as x, y. In projective geometry, we use the homogeneous coordinates x, y, w. So where the triple is defined up to a scalar multiplication. That is, this triplet is equal to kx, ky, kw, where k is any non-zero constant. So points where this w is 0, they lie on line at infinity, and the points where w is not equal to 0, they lie in affine plane, and w is equal to 0 implies line at infinity. So as we saw earlier, line at infinity can be algebraically defined as L infinity is equal to x, 0, and this belongs to p square. So it contains one point for every direction in the affine plane and ensures that all lines in the projective plane intersect, even those that are parallel in affine plane. Now we look at the geometric construction. So geometrically, the line at infinity arises when we complete the affine plane by adding points at infinity, one for each family of parallel lines. So parallel lines in the same direction are assigned a unique vanishing point. These points collectively form the line at infinity, a new line added to the plane. This idea is visually evident in perspective drawing, where parallel lines like railway tracks uh, in real life appear to converge at a distant point on the horizon. That horizon corresponds to the line at infinity, and each direction has its own vanishing point. So this construction leads to the projective plane, where all lines, including parallel ones, meet exactly once, either at a finite point or at a point on the line of infinity. So if this is the horizon, all the lines will be meeting on a point at this horizon. This is the vanishing line in most of the drawings and even the pictures that we take. Yeah. So, and the third and last way is the way via duality. In projective geometry, duality states that every theorem involving points and lines has a dual version with the roles reversed. For duality to work, every pair of lines must intersect something, uh, which is something not true in affine geometry. To restore this symmetry, parallel lines are defined to intersect at ideal points on the lines at infinity. These points preserve the incident structure needed for duality. Thus, the line at infinity is necessary for maintaining the logical and structural balance of the projective geometry. It allows the full interchangeability of points and lines in theorems, turning geometric reasoning into a more symmetrical and powerful system. Can you guess what is the dual of line at infinity? It's actually the origin point itself. Rishit is close, it's the point itself. Origin is considered the dual of line at infinity. So, well, that was a lot. Now we'll take a short break and then Smithali will continue the session further. In the meantime, feel free to ask any doubts which you have.
Also, in the short break, again put your names in the chat for attendance.
For attendance.
Yeah, okay, cool. So now I'll take a brief recap of what Bhavi explained about projective space. So firstly, let's focus on one-dimensional projective space. What's different in one-dimensional projective space than 1D real space or complex space is that you need infinity. So basically, it's just the real line. If you consider RP1, that is real projective plane in one dimension. It's basically the real line with infinity included. If you consider CP1, it is the complex plane with infinity included. Now, complex plane, but it is still one dimension. It's just how complex numbers behave, right? So yeah, that is what a projective line would look like. Uh, then coming to projective space. So if you want to represent the 2D projective space, if you want to visualize it in 3D space, what you do is you take the union of R3 and infinity. Uh, now, consider this. You have 0, 0, 0. Would 0, 0, 0 belong to the 0 class or would it belong to the infinity class? Because it is 0, 0 in x and y, and you have the third 0, which corresponds to the infinity class. So that's a confusion. That's why what they thought was we'll just exclude x comma y equals 0, 0. So here it says xyz so is similar to lambda x, lambda y, lambda z for lambda not equal to 0 and also for x comma y not equal to 0. Now, if you want to visualize R2 in P2, R2 in RP2, you basically put z equals 1. So, any point, like if you just remove the z coordinate x comma y comma 1, and so x comma y would be its equivalent in R2. Uh, Coming to transformation, so we know what Euclidean transformations are. Like you have three, any Euclidean transformation is composed of three transformation: translation, rotation, and reflection. So, uh, like given any Euclidean space, you perform these three transformation, it will still be a Euclidean space. Now, how do we define a projective transformation? That if I perform this projective transformation, whatever might happen, it will still hold all the laws of the projective space. So for projective line P1, as Bhavi said, projective transformation is defined in this way. And if you want to visualize it as a matrix, consider the ABCD matrix and x1, x comma 1 be the projective point on that line. So AX plus B, CX plus D is the transformed version of it. So basically you have the point x1, you transform it to ax plus b, cx plus d. Uh, Similarly, okay, so here is an example for 3D transformation. So if you have x, y, z, you perform a three-dimensional matrix over it, matrix multiplication. You get x dash, y dash, z dash. Let's do it again. This is just projecting and then line. Okay, so something interesting over here is that lines remain line, right? Uh, Wait. So, like when you are doing this projective transformation, can any point get converted into any point, like by a matrix multiplication? The answer is no. Like, as you saw in the previous animation, lines remain lines. Like if some points lie on a line, they lie on the same projected line. Uh, Another thing is you can now if this Z, if you map, if you construct this matrix such that this Z gets mapped to 0, so you can convert, you can project any finite point onto a point at infinity. So that's there, and it distorts angles, length, and parallelism. Like obviously, this is distorting angles, length, and parallelism both because these spiral lines will now converge at infinity, and this length is also distorted, and obviously the 90 degree is not 90-degree anymore. So coming to cross ratio. So in translation, angles are preserved. In rotation, length is preserved. So, what operation remains preserved under projective transformation? Because in projective transformation now, angles, length, in fact, even the point at finite points become infinite points. So, what would remain preserved? Why is this important? to to group any similar projective space as similar, you need to have one such operation. So like if I can say like this is just performing this operation on the original space, and that's why they are just the same. All the properties are going to be the same. So that's why you need a invariant operation. So this operation is basically the cross ratio. So coming to one dimensional projective space, if you have A, B, C, D are four coordinates on R union infinity, so their cross ratio would be AC into BD upon AD into BC. What this basically measures is how close are these points to one another uh, with respect to the perspective they have. So to understand this better, uh, here basically you have points A, B, C, D, and this point P. So you draw lines from PC to extend it. Here C dash, what C dash is? It's intersection of the extended PC with this line. Similarly, PB intersection of extended PB with B dash on the with this line is B dash, and so on. So the original cross ratio is the cross ratio on this line, and the projected cross ratio is the cross ratio on this line with respect to P. Like P is the point around which you are projecting. So yeah, here is an animation. So how much, however I project, the cross ratio given the points are same remains same. So yes, and scan this question for answer. Hmm. So only 6 people have joined. Interesting. Okay, so yeah, the answer is right. Z equals 1 points corresponds to points equivalent to real plane, like as I already said previously. So yeah, this is about cross ratio. Coming to application, so cross ratio has obviously cross ratio forms the entire of measurement distinct measurement you have in projective geometry. So I'll talk about its application in computer graphics and computer vision. So the first thing you see here is you visualize you give the uh, you give the system a 2D image, and that using the uh, keeping the perspective ratio constant, that gets changed into a 3D image. And next like this is 2D to 3D, and in computer vision, so basically like you see images where things meet at infinity, or uh, so basically, to have the notion of infinity, like what it actually, like what the image actually is, it's not really meeting at infinity, right? So that's another application. So this, oh wait. So this basically, this is a project, easy project you will also see on GitHub. I have attached the link. We'll share you link to the slides later. So what this does is it projects a real world 3D playground to a two-dimensional image on your computer, and if you click on any places, you see the real coordinates of it. So as you can see, like the distances are real. Uh, yeah, this is one example of projection of like using keeping the perspective ratio same. You project from 3D to 2D, and it is also used in many other places. For example, in shopping platforms, in some shopping platforms, if you upload your image, it will convert your image into a 3D body, and then if you just choose some random clothing, and then if you choose some random clothing, you can put them on yourself 3D and see how it looks. Or it's used in tiles industries and all. So yeah, those are pretty good applications of projective geometry in CV, and Bhavi will take over now for other applications.
So now let us continue with the application of projective geometry. Yeah. So, in architectural designs, architects rely heavily on perspective drawings to communicate spatial ideas. These designs are grounded in projective geometry, which formalize how 3D objects project onto 2D surfaces. By using vanishing points where parallel lines in projector space appear to converge, the designers stimulate depth and scale in architectural rendering. So the first image, this one, is an example of one-point perspective. So one-point perspective involves a single vanishing point for lines receding in one direction. So this second picture, it is an example of two-point perspective. It handles corner views where two sets of parallel lines vanish in different directions. This is an example of three-point perspective. It introduces vertical depth, showing objects from high or low angles. As we can see, it tries to visualize how tall the building is. So that is three-point perspective. Then these practical implementations of projections from 3D space onto 2D plane, typically using the rules of central projection. The concept of line at infinity is reflected in the horizon line where all the vanishing points lie, ensuring that all the parallel lines have a meaningful point of convergence. This geometric clarity helps clients and engineers understand the building's form, spatial relationships, and how it will interact with its environment long before it is constructed. Now, modern computer-aided designs or CAD software uses homogeneous coordinates and projective transformations to render three-dimensional models accurately onto 2D screens. As you can see here, this is an example of a CAD drawing which is made keeping in mind the projective perspectives. So transformations like translations, rotating, scaling, and projections are all performed using matrix operations, which are linear in homogeneous space. For instance, to project a 3D object onto a 2D viewpoint, each point is represented as x, y, z, w, and then the projection matrix transforms these to 2D screen coordinates. So points at infinity, where w is 0, correspond to directions and vanishing points. Now, projective geometry ensures that these renderings preserve straight lines, incidence, and convergence, which is vital for realism. Features such as perspective correct texturing, camera simulations, and shadow projections all rely on projective mathematics. Last is restoring and reverse engineering. So, in architectural conservations, projective geometry allows for the analysis and reconstruction of historic buildings from old photographs or paintings. By identifying vanishing points uh, and lines in perspective drawings or images, it's possible to reconstruct accurate dimensions and spatial configurations of structures. For example, this photograph obliquely can be evolved by mapping its lines back to their ideal geometry using projective transformations. This is invaluable when blueprints are missing or when buildings have suffered a lot of damage. Lastly, in art and visual representation. During the Renaissance, artists systematically applied projective principles to create realistic depth in two-dimensional artwork. Painters began using vanishing points for consistent depth, transversals and orthogonals to construct tiled floors, arches, and cityscapes, and foreshortening to represent objects at angles. All these constructions depend on understanding how 3D geometry projects onto 2D plane. What appears natural in perspective art is in fact governed by rigid projective rules. The artist chooses a viewpoint, which is I, and construct rays from the eye to the object, and then marks where they intersect the canvas, and that is the picture plane. These central projections mathematically defined by the projective transformations. Artists exploring urban or interior scenes use 2-point or 3-point perspectives, adding more vanishing points to depict depth in multiple dimensions. Projective geometry provides the theoretical justification for these constructions, ensuring that spatial relationships remain internally consistent. As we can see in here, the buildings they provide a very clear view of the depth of them, like how long the corridors are and how far away they appear. In photography, a camera models pinhole projector, which is physical realization of central projection in projective geometry. Light rays from a 3D scene pass through a single point, the pinhole or lens center, and intersect a flat surface, which is the image sensor or film, and this result is a projective image of the real world. Each point in space is mapped to a point on the image plane via a projection, and this transformation is mathematically modeled by a projection matrix in homogeneous coordinates. The use of projective geometry in camera modeling allows for accurate analysis of perspective distortion, lens calibration, depth recovery, and in professional photography and cinematography, understanding how objects uh, project into the camera frame help in composing shots with desired spatial effects, managing depth of the field, and predicting line convergence. So, lastly, can you spot what is wrong with these images? Answer in chat. Yes, Vishwa, this is correct. So basically, all of both of these paintings, their perspective, their perspective is wrong. That is not correct. All of them have a flaw in their perspective. Do you guys have any doubts or want any concepts to be explained?
Yeah, so we have buffer time. So if you guys have any doubts or any topic particularly interests you more and want us to speak more on that, put that in the chat or unmute. Yes. Yes. So the point P in the cross ratio thing. So like what I wanted to show is that even if you project it, even if you project that like the line to another line. So if you want to project it, you will have to keep something constant, right? So the other basically the projection, basically the projections of the those points A, B, C, D on the other line were A dash, B dash, C dash, and from where do you project? You project the from point B. Is that clear? Wait, I'll share screen. Yeah, so basically, so what point P is, you take PC. its intersection with this other line is C dash. You take PB, its intersection with this line is B dash. So in this way, the ABCD and A dash B dash C dash D dash will have the same cross ratio. Then what we do is we change these points of projection, like we change P to various places. The cross ratio changes for both of them, but it's the same of both of them. Saying that the cross ratio is invariant across projections. Is that clear? Cool.
I think you're on mute.
Yeah, like any other doubts or anything which interests you in particular. Okay, so the credits for this particular visualization goes to Cloud4. You just ask it to give you a cross ratio invariance visualization. It will give you the HTML code. Copy paste that code, I guess. Okay, so the football field example. Uh, okay, so the idea over here is now, so this is a 2D image, right? So, like for example, this length which you see here, it is also inclined and it is also small. So, if you consider the real 3D world, if you keep the perspective ratio same, so like here what we did was like through point P you project. So consider this is your 2D line and this is the real line in 3D world. So if you basically have the same point P and it's just the projection of the other, the cross ratio will remain the same. So if this is your 2D and this is your 3D line, uh, what we do is we keep the cross ratio the same and then you project from 3D to 2D. So what this project did was they wrote a JavaScript code to basically just keep the cross ratio invariant. And if you give it any 2D image, it will give you this kind of mapping for 3D images. Like it will give you the real 3D world coordinates. And then this is one example. If you want the link, I'll drop the link for this too. Wait. Does that help? Okay, so since there are no more doubts, we'll give you a bit of spoilers. Okay, wait. Is there a orientation constraint when working with causation? So essentially, causation. Yes, I think yeah, that's right. You are viewing the field from point P, and the real coordinates are projected to the 2D view, which is visible to you. Yeah, that's it. So like this thing. Yeah, this thing here. That's exactly right. Point P is the eye over here. So what I was saying is, yeah, if you have any doubts, put the doubts. And apart from that, if you want to know how the assignments are, so basically in assignments you will have to do the things taught for various kind of projective and affine planes. For example, ZP2. What ZP2 is, what uh, basically ZP is like subscript P, which means 0 to P minus 1, the natural numbers from 0 to p minus 1, basically numbers which you get remainder after you divide by p. So you have to prove stuff and give the like how a fine plane works in ZP2, ZP3, and so on. And apart from that, you have to also deal with complex plane, like how would CP2 look? Like I said, right? You have RP1, you have CP1, but CP1 is actually a plane. So yeah, okay, theory of congruence is next session. So you will be able to do the assignment better after that. So if you also get any doubts in the assignment, you can ask us. Like we have provided our numbers. At 10:45, we'll give you a summary of the session. Before that, if you have any doubts, put it in the chat. No, you will get a assignment fee. Yes, the recorded video will be there on Math Club YouTube channel. So subscribe the YouTube channel. Okay, cool. So let's have a summary of the session. Uh, like participants volunteer to, okay, we'll break the session into three parts. One, the axiomatic part. Uh, second, the measurement and theoretical part. And third, the application. So someone volunteer to do the first part. If you volunteer, you get brownie points for your assignments. So yeah, just raise your hands or unmute. Okay, right. So for so initially what we saw was the how you have the set of axioms for Euclidean geometry, and if you remove the parallel axioms if you remove the parallel axioms, you come up with a set for projective geometry. All and the set of axioms, um, while they are necessary and sufficient, you can take intersections and unions of axioms and create a different equivalent set of axioms, which are more readable, understandable compared to the initial set of axioms. What The axiom of interest in the projective geometry was uh, was the second axiom, which says that any two lines are always incident at one point. So there are no parallel lines, and the supposedly parallel lines from Euclidean plane do meet at a point at infinity. And for all such some points at infinity, if you combine them, what you get is the line at infinity. Now, someone volunteer for the theoretical part, which Bhavi and the Bhavi covered about affine planes and projective plane. Okay, right, I guess. Bobby, you can give the summary for Affine plane.
Yeah. So, uh, yeah. So basically, we discussed what are homogeneous coordinates, how are they different from Cartesian coordinates, how do we present points, lines, and do transformations using them. Then we moved on to affine plane, discussed its properties, how do we present it, uh, how it is different from both projective plane and Euclidean plane. Then we moved on to line at infinity. What is it basically? How does it help in establishing duality? And the properties of it. How do we present points lying on line at infinity, the dual of it? We so that was the basic one. Anyone wants to elaborate on that? Any particular topic? No? I guess we can move on to application.
Okay, so in applications, the first application was basically based on cross ratio invariant. So you project from 2D to 3D, or in 2D itself, you uh, you understand what something converging at seem to converging at infinity means by keeping the cross ratio invariant. And then we talked about the applications in arts and photography. So yeah, that was the summary.
Give your thoughts on the session. Like, did you like it? Or was it boring? Anyone?
All right. Okay. Before we go to some reviews, maybe I'll elaborate on one sort of personal experience I have with projective geometry. So I dabble a lot in the space of computer graphics, and this application might be useful to a lot of engineering fellows. So the okay, a lot of you would have at some point of time in your life played video games, and it is kind of fascinating how you are able to project an n number of 3D models with possibly millions and millions of triangles all into just one tiny screen of yours, and that too in real time. Each frame is usually rendered in around 16 milliseconds or so, and then blitted onto the frame before you see it on your screen, and so on and so forth. But think about it. You have about a million or more triangles that need to be processed. They then have to be colored. You need to do depth testing and all of that. And yet, even if you have a very good GPU with around thousands of cores, you're able to do millions of such calculations in real time. And one very important thing that comes into play here is projective geometry. So I'll take you through how the rendering workflow goes. So let's say you have some million triangles in your scene. The way usually game engines center things are, you pick up each vertex, you use some projective geometry techniques to convert the space in 3D space to a space called the viewing frustum, and this transform is an affine transform. Now, again, what you do later on is you apply a perspective projection to ensure things look just like how humans see things, and all of these are just matrix multiplications, since again they are linear transformations. Now, with the additional information of just depth, what you can do is so this vertex shader runs for each vertex of each triangle, but before you pass it on to the fragment shader, which does the job of converting each vertex into possibly a pixel that will show up on your screen. So already you have around 3 million things to be processed. You simply do a check called depth testing followed by vertex culling. So again, I'll put the keywords in the chat. Culling, yeah, viewing frustum. So, and depth testing. You can actually just go on after the session, look at how these algorithms work. And so, just this very basic idea in projective geometry, when translated into code, lets you eliminate upwards of around 2 million calls that were previously needed, and you just have in the order of 1,000 calls which have to be processed by the fragment shader later on to convert the actual vertex data into pixels that appear on the screen. Now, while this was one application in computer graphics, this approach usually can be taken in anything that involves a rejection of samples. So even if you're dealing with Monte Carlo techniques for some financial model that you're cooking, the thing is, if your algorithm is generating a lot of samples which will be rejected later on, if you are able to wrap them up in a very nice space and apply the same techniques there as well, then you get to reject a lot of samples early on before processing them and then realizing later on that they are not useful. You could use the same thing to any sort of application in engineering as well, where the abundance is in the data. You have a lot of data. You know for a fact a lot of it isn't going to be useful at the end. But if you are able to construct a nice space out of the data and then apply these techniques, you will be able to reject a lot of the samples early on before you start processing them. So that's just a nice tidbit. If any of you want me to expand more on some of the things that I said, then sure, I'll be happy to. If not, we'll just get some feedback on it. Yes, please. What exactly would you like me to expand upon? All it. Okay. So, I'll maybe link to some articles in the WhatsApp group. So the basic procedure is as such. Basically, so again, okay, let's take this as an example. Let's say you have some random process, which is driven through a bunch of samples. Now, let's say you have this gigantic function f, which takes in some 100 numbers, x1, x2, x3, x4 up to x100. And your job is to process this function f up to some certain stage. Now, instead of go looking at the properties of the evaluated function f, what you do is you assume these variables x1 to x100 to be a part of a 100-dimensional space. You see if this data fits certain criteria for it to be a valid space, as basically the axioms that were taught today, but extended to higher dimensions. You then apply the same tests that you would to sort of see if a point is visible or not, which would translate to your sample being useful or not. You need to define that mapping. If you are able to find such a mapping, then you simply cull away the points or the samples beforehand, the 100 values that you have generated, before sending them off to the parsing function f. Now, again, this is just a boilerplate template. F could be basically anything that suits your purpose. But again, all of this holds if you're able to find that mapping correspondence between f being a valid sample and your samples, the points that you picked, x1 to x100, they themselves too, whether they should be culled or not. There's this thing called, I don't remember its name. Okay, like, yeah. If I remember the name of the algorithm, I'll share it on the WhatsApp group.
Okay, one interesting question is, you saw like we have points at infinity and all. If I want to say know whether there is a like if I want to find the a number some number at infinity, say for example prime at infinity, like can you somehow construct some geometry in which you define like you had this in which you classify types of primes using homogeneous coordinates, and then you define a notion of prime at infinity, and basically a class would correspond to prime at infinity. For this, what you do is instead of taking the field to be R or C, you take it a prime field. So you can also look up on this if you are interested. And like interestingly, number theory and like number theory project like affine geometries and all, affine geometry and topology, all these three fields interestingly come together. Yeah, so that's a interesting question, like the notion of prime at infinity. So you can prove some number theoretic theorems uh, or unproven theorems using using geometry as well.